People have had 5 minutes to get here. Let me just get everything working. So I'll go over the announcements. First of all, the first set of worksheets and homework are due on Thursday this week, the 11th. They're due on Brightspace, or if you want, you can turn them in person in class for the homework. The worksheets you obviously have to do on Brightspace because the quiz is on Brightspace. But for the homework, you can either submit it as a file on Brightspace to the assignment for the homework, or you can turn it in on paper in class. It's your choice. Our first test on chapters 1 through 2 and 5 through 7 will be on Thursday in class. You need to be here. It'll be 60 multiple choice questions. You get one sheet of notes to use for reference. You can use that as for notes. It will use a Scantron sheet. So you'll need a pencil. I will have some extra pencils, but you will need a pencil. And you need to be in class to take the test. You cannot take the test remotely. And lastly, make sure to sign in on the sign-in sheet for attendance purposes. But we will have a test on Thursday. You do need to be here. We will be using a Scantron sheet, so you should bring a pencil. I will have some extras, but it's best to have your own. Any questions? Yes. It'll be the entire class period. So all we're doing on Thursday is taking the test. So an hour and 20 minutes. Any other questions? Just.
Do you gotta be like, are you gonna head out or?
Yeah, if you're finished, you can have. That's how it would work out. That's all you usually do tests, just because there's no purpose in sitting around doing it. So do remember you need to be here in person to take the test on Thursday. I put an announcement up on Brightspace. It'll come up around the end of class. Just as a reminder. Yeah. I think that's all the questions. Oh, and lastly, I will be curving the test because yeah. So we're going to finish off chapter 7 by talking about the formation of the solar system. So we can learn about the solar system by looking at the patterns that still exist in the solar system today. So some examples of this are all the planets orbit in approximately the same plane. The solar system is flat. All the planets orbit around the sun in more or less the same direction. Most of the planets also rotate around their axes in that same direction. The planets are separated by a type into two types, terrestrial and Jovian, and there's lots of small bodies in the solar system, things like asteroids, comets, etc. So we can break these features down and try and think about what leads to them. I think this is good. Yeah.
This cosmic context figure from your textbook summarizes 4 major features of our solar system that must be explained by any theory that seeks to describe how our solar system formed. The first major feature is that the large bodies of our solar system have orderly motions. This oblique view shows that the planets all orbit the sun in the same direction, counterclockwise as viewed from high above Earth's North Pole, and in nearly the same plane. Switching to a top-down view, we also see that although planet orbits are elliptical in accord with Kepler's first law, these ellipses are very close to being circular. Moreover, the small white arrows indicate that, with the notable exceptions of Venus and Uranus, most planets rotate in the same counterclockwise direction that they orbit the Sun, and the red circles show that major moons generally orbit in their planet's equatorial plane and in the same direction that their planet rotates. Before we continue, think back on what you've learned about the laws of nature to answer this question. Notice that the Sun also rotates in the same counterclockwise direction that the planets orbit. What law of nature explains why the Sun should have been rotating after it formed from a collapsing cloud of gas? Is it the law of conservation of angular momentum, the law of conservation of energy, the universal law of gravitation, or Kepler's first law of planetary motion? The answer is A, the law of conservation of angular momentum. This is because a collapsing cloud, almost inevitably, will have some small net rotation, so as it contracts in radius, its rate of rotation must speed up. In fact, the Sun probably once rotated much faster, but has transferred angular momentum over time to the planets and to interplanetary gas. Moving on, the second major feature is that the planets fall into two major categories, which we call terrestrial, which means Earth-like, and Jovian, which means Jupiter-like. In our solar system, the terrestrial planets are the four inner planets, Mercury, Venus, Earth, and Mars, and we generally count our moon as a fifth terrestrial world. The Jovian planets are the four outer planets, Jupiter, Saturn, Uranus, and Neptune. They are actually much larger in comparison to the terrestrial planets than shown here. Comparing the categories more generally, the terrestrial planets are small in mass and size, relatively close to the Sun, made mostly of metal and rock, and have few moons and no rings. In contrast, Jovian planets are much larger in mass and size, orbit far from the Sun, at least in our solar system, are made largely of hydrogen, helium, and hydrogen compounds such as water, methane, and ammonia, and those in our solar system all have rings and numerous moons. The third major feature is that in addition to the planets, vast numbers of small bodies also orbit the Sun, represented here as swarms of individual dots. We generally call these asteroids when they are rocky in composition, and comets when they are ice-rich. Some of these small bodies are large enough that we call them dwarf planets, as is the case with Pluto, Eris, the asteroid Ceres, and a few others. Most asteroids and comets are found in three major regions of the solar system. Asteroids are concentrated in the asteroid belt between the orbits of Mars and Jupiter. Most comets are found either in the Kuiper belt that lies beyond the orbit of Neptune, or in the far more distant region we call the Oort cloud, which is roughly spherical in shape because its comets have orbits that are randomly inclined to the ecliptic plane. Our fourth major feature is that there are a few notable exceptions to the general rules described in the first three features. For example, while most planets rotate in the same direction as they orbit, Uranus rotates nearly on its side, and Venus rotates backward compared to its orbit. Another important exception concerns our own moon, which is the only large moon found around a terrestrial planet in our solar system. As you will learn soon, the quest to explain these four features led scientists to our modern nebular theory of solar system formation, a theory that not only explains the origin of our own solar system, but also explains the many other planetary systems now known to exist.
This is sort of an overview that you can look at on your own time. So all large bodies in the solar system orbit in the same direction and in nearly the same plane, and most of them also rotate in that same direction, with a couple of exceptions. So pretty much everything is all going around the same sun in the same direction the sun is rotating, and everything also rotates in the same direction the sun is rotating. There's two major planet types. The terrestrial planets, which are rocky, relatively small, and close to the sun, and the Jovian planets, which are gaseous, larger, and further from the sun. And there are several exceptions. So the two planets that rotate the wrong direction are Uranus, which is on its side, and Venus, which rotates very slowly backwards. Earth has an excessively large moon. There's a few exceptions. So if we look at these patterns, we can put together a model based on these patterns. So everything probably started as the same stuff because it's all spinning in the same direction. There's a bunch of little bits around. Those are probably leftovers. So there was some stage where we had smaller pieces that glommed into bigger things. Yeah, you can sort of work this out. So this lets us work out a nebulae theory where the solar system started as a large cloud of gas and dust that collapsed. So it formed from a giant cloud of interstellar gas. A nebula is a cloud. This is a nebula lit up from within. And the cloud that formed the nebula was the remnants of previous stars. We know that because the elements that make up us and Earth and things like that had to have, the only way we know how they could be formed was in stars. So stars lived, died, exploded, their remnants collected into a nebula. Eventually that nebula died, collapsed, sorry, not died, collapsed, becoming the solar system. Something happened that caused it to get dense enough to collapse. So the solar system formed from a large cloud of gas and dust, mostly hydrogen gas, because most of the universe is hydrogen gas, that started collapsing around 5 billion years ago. The rotation of that cloud is reflected in the motions of the planets today. Everything is still rotating in the same direction that cloud was rotating, just faster. The hotter temperatures near the sun would have caused different types of material to condense. So basically, close to the sun, it's warmer. So things like ices couldn't become solid. And so you got rocky, small planets. Further from the sun, it's colder, so ices can be solid. So you got bigger planets, which eventually could grab onto gas and become large and gaseous. And the small bodies are leftover remnants of planetary formation. So part of the reason we're interested in studying things like asteroids and comets is because they're leftovers from the formation of the solar system. So they give us access to very early, unmodified materials from the early solar system. So there's a large cloud of gas and dust that something happened to cause it to get dense enough to collapse under its own gravity. It could have been a nearby exploding star compressing it. There's a whole bunch of things that could have happened. It contracts due to gravity, and the conservation of angular momentum means it spins faster and faster as it contracts. Most of the material collapses into the middle, but it does, as it spins faster, it spins out a disk, like a frisbee shape. So there's a hot, dense region in the middle, a bulge, and then a flat disk across. And as the gas cools, it changes its state to become tiny solid particles. Interstellar dust grains would act as condensation nuclei around which this material could condense. And so eventually you go from this disk-shaped cloud, where you have hotter regions and cooler regions, things start to form. You get rocky planetesimals in the hotter regions and icy bodies further out. And then those planetesimals condense to form larger bodies. And eventually you get the solar system of today. So, angular momentum. Conservation of angular momentum says that the product of your radius and your rotation rate needs to be constant. So as you move your mass inwards, to keep your angular momentum the same, you have to spin faster. So as a dust cloud collapses, its rate of rotation will increase. This is what you see with figure skaters when they do a jump. They start with their arms and legs out, and then and start spinning with their arms and legs out. And then they pull their arms and legs in to spin faster. Divers do this as well. They tuck into a ball to rotate more quickly before they extend to plummet into the water. Because you can control how fast you rotate by how extended you are. So this is a short video about the nebular hypothesis. And yeah, the formation of the planets from a nebula.
Formation of the planets. The universe comprises countless galaxies, each one containing numerous stars. Around some of those stars, there are planets, just like those that orbit our own star, the Sun. The nebular hypothesis is the most widely accepted explanation for how the Sun and planets in the solar system may have formed. When our solar system was first created, all that was thought to have existed was a cold, spinning cloud of gas called the solar nebula. The nebula resulted from an uneven distribution of gases throughout the universe. As the gravitational pull began to condense the gas toward the center, the speed of the rotation increased. This caused the cloud to flatten, creating an accretion disk. Matter continued to collect as the growing force of gravity drew it toward the center. Eventually, the gas warmed from the increasing pressure. As the mass further increased, the gravity also increased, and as a result, the temperature continued to rise. A ball of hot gas formed in the center of the accretion disk, creating a protostar, also known as the Sun. Finally, when enough gas gathered in the center of the protostar, the pressure generated enough heat to fuse the atoms, forming a star. Outside the star, matter was forming into clumps of gas, dust, and rock, which created protoplanets. These protoplanets continued to grow as they trapped material in their gravitational fields. Because the protoplanets all formed from the same cloud of gas and dust, they travel around the Sun in the same direction and in the same plane. The nebular hypothesis also explains how the planets are arranged. The heat and solar winds caused by the Sun swept the lighter gases farther out into the developing solar system. This is why the rocky terrestrial planets, Mercury, Venus, Earth, and Mars, are located closer to the Sun. The gas giants, Jupiter, Saturn, Uranus, and Neptune, formed in the cooler outer region of the solar system. The solar system continued to evolve even after its initial formation. Large asteroids slammed into planets, and the planets themselves differentiated into layers as they slowly cooled. Although the nebular hypothesis cannot be directly tested, it is a useful description for how a solar system forms. It explains why planets and the star they orbit usually spin in the same direction and lie in the same plane. It also explains the arrangement of the planets, with the rocky planets nearest to the Sun and the gas giants farther away. The next time that you look at the stars twinkling in the night sky, imagine new planets forming using these very steps.
It's also been somewhat backed up by the fact that we've observed places where stars are forming and they're, spinning clouds of gas with a protostar in the center. But there are actually a couple of issues with our current model. It's really good for our solar system. It doesn't explain all the exoplanets we've found. We've found some exoplanets that don't match up with our current model of solar system formation. Specifically, we found what are called hot Jupiters, which are really big planets that are clearly gas giants that are close to their stars, where it would, according to our normal theory, be too hot. So, we need an explanation for those. It's something people are working on. So, as the solar system formed, as the nebula began to cool, particles begin to condense into larger objects, things like grains of sand, pebbles, small rocks, bigger rocks. And over millions of years, these slowly grew out larger, eventually becoming the planets we see today. And then in some places, they never condensed. Like the asteroid belt, well, there's not actually that much stuff in the asteroid belt, but there are actually reasons why the asteroid belt stays all spread out like it is. It interacts with the gravity of Jupiter. So once Jupiter formed, it prevented anything from condensing in that region. And temperature in the cloud determines where various materials will condense out. Where it's hot, you get stuff with high melting points, like rock and metal. Where it's colder, you can get stuff that's got lower melting points, like ices, water ice, ammonia ice, carbon dioxide ice. And so out further from the sun, there are more materials you can make planets out of. So the core can get bigger and it can reach the critical point where the planet is big enough to hold on to light gases. And once you can hold on to light gases, you're real big. So, as you cool, you get larger. And as planets form, they clear out the remaining debris. Some of that debris becomes part of the planet. Some merges into the planet. Some just gets knocked out of its orbit and ejected out into interstellar space. But in the orbits of the planets, they dominate. There's very little else in the orbits of the planets. And once the sun fully forms, the solar wind and radiation pressure will clear out the remaining gas and dust. The solar wind is an outflow of particles from the sun. And radiation pressure is pressure from the light of the sun. So once the sun starts pumping out steady energy from fusion, it's going to start pushing everything light away. And that clears out the remaining gas and dust, and we're left with our current modern solar system. And we can look at other gas clouds. We can look at stars forming in other interstellar gas clouds, in other large nebula out in space. So here is the Orion Nebula, and each of these insets is a solar system forming, a nascent solar system forming. So these are places where stars are being born. We see protostar in the center, disk of dust and lighter material around it. So here we know many planetary systems outside our own. Planetary systems are very common. And here we see, stars forming. There's this disk of material around it. Dusty disks around stars. So what we're probably observing is the process of planetary formation. Because everything takes a very long time. This process takes millions of years, but we can observe it happening at various stages in the process. So we now know of many planetary systems outside of our own. More than 5,000 as of 2023. So lots of them. So this is a planetary system other than our own. We've detected dusty disks around stars. So here is Beta Pictoris with a disk of warm matter, which can indicate planetary formation. And in very rare cases, we can see the planets. That's this one, which is HR 8799. So here we have a dusky disk of matter around the forming star. Here's some possible planetary systems in the process of formation. You know, star in the middle, disk of material around condensing. Here are some known exoplanets, and Neptune and Earth. Generally, we've found planets that are close to their stars and large. That is not probably a function of how planets are distributed throughout, the galaxy. It's more a function of that makes them easier to detect. The bigger a planet is and the closer it is to the star, the easier it is to detect. Because our planet detection methods are generally based on, watching closer a planet is to the star, faster it orbits. So the less time it takes to record enough data to see that there's a planet there. And then the bigger it is, the bigger effect it has on its star. So it's going to have more signal. So some planets are discovered through the wobble they create in their parent star's orbit. So as the planet orbits, the star also orbits the mutual center of mass. So it's going to move in and out. And that's a bigger effect the closer and heavier the planet is, basically. Well, the heavier the planet is. Another way is that when a planet passes in front of a star, it causes the star to dim slightly. So again, bigger effect when the planet is bigger. And so here are some examples of many of the extrasolar planets discovered so far, and most of them have masses closer to Jupiter than to Earth. Again, this is probably biased from our detection methods. We have found stuff on the scale of Earth, roughly. But yeah, it's easier to detect stuff close to the star. It's easier to detect stuff that's more massive. But yeah, we found thousands of them because there's some satellites doing like continuous surveys to detect exoplanets. So here is a plot of the masses of many extrasolar planets found so far. Here you can see the distance from the sun and the mass. And you can see how most of them are much more massive than Earth. But in all likelihood, this is, and then up above this line, you get into brown dwarfs, which aren't planets anymore. But yeah, most of what we've detected is sort of in the Jupiter, Neptune range. And fairly close to their stars. It's an issue with our methodology, mostly. So we can look at the patterns that exist in the solar system today to understand how it formed millions of years ago. And a large cloud of gas and dust collapsed to form our solar system. And we see evidence of this occurring today around other stars. So in summary of chapter 7, solar system consists of the sun and everything that orbits it. Asteroids are rocky and most orbit between the orbits of Mars and Jupiter. Comets are icy and believed to have formed early in the solar system's life. The major planets orbit the sun in the same sense, and all but Venus rotate in that sense as well. And the planetary orbits lie almost in the same plane. The 4 inner planets are rocky, small, and dense. The 4 outer planets are made of gas and liquid and are large. And the nebular theory of the solar system formation says a cloud of gas and dust gradually collapsed under its own gravity, spinning faster as it shrank. And condensation theory says dust rays acted as condensation nuclei, beginning the formation of larger objects. And planets have been discovered in other solar systems, and most of those discovered so far are large and orbit much closer to the sun than the large planets in our solar system do. And that's one of the things we're trying to understand. Clearly, a lot of these hot Jupiters exist. We're trying to understand what's going on with them. So just another reminder for anyone who got here a bit late. On Thursday, we will be having the test. It's multiple choice using a Scantron, so you need to have a pencil. It will be in class for the entire class period. It's 60 multiple choice questions. Now I'm going to start chapter 8 and 9. And talk about Earth and its moon. Why are you being? Let me Oh no, when did I get muted? Um. Uh, well, I'll go over this again real quick just to make sure. I'm not sure how I got muted. So, quick review, unique properties of the Earth. It's the only planet with liquid water on its surface. It's the only planet with oxygen in its atmosphere, and it's the only planet known to have life. I'm sorry that got muted, and I'm sorry about the muting in the recording. I'm not sure how that happened. I must have bumped something. Uh, the crust is the surface layer with the lightest materials. The mantle is molten or semi-molten materials. And the liquid outer core is molten iron and nickel, while the solid inner core is solid iron and nickel. And while we can't drill to the Earth because it's just too far, we drilled, the deepest we've drilled is about 12 kilometers, at which point the drills kept melting. At the distance to the core is about 6,000 kilometers, so we're barely scratching the surface kind of thing. And we never even made it through the crust. So we need to use indirect observations. So we use earthquakes, which act like an ultrasound, where they send out waves of essentially sound, two types of waves that travel through the interior of the Earth. And if we observe how those waves get bent and absorbed, we can get an idea of the interior structure of the Earth. Combined with measurements of magnetism and gravity, we can get ideas about the distribution of matter within the Earth. So earthquakes produce both pressure and shear waves. The pressure waves will travel through both liquids and solids. The shear waves will not travel through liquids, as liquids don't resist shear forces, and the wave speed depends on the density of the material. And when you go from one speed to another, that bends the wave. So pressure waves are like sound waves. They're longitudinal. The particles move in the same direction that the wave moves. While shear waves are transverse, they're like waves on a string where the particles move perpendicular to the direction the wave moves. So if the wave is moving forward, they could move up and down. While for a pressure wave, if the wave is moving forward, they will move back and forth. We can use the pattern of waves measured by seismometers during earthquakes to deduce the interior structure of the Earth, to figure that out. The currently accepted model has solid inner core and liquid outer core that are much denser than the mantle above it. Density generally steadily decreases as you go out towards the edges, as does temperature. But there's a sharp transition between the core and the mantle, because the mantle is much less dense than the core. The mantle is rocky while the core is metallic. The core is made of iron and nickel. The outer core is liquid, the inner core is solid, and volcanic lava comes from the mantle, allowing analysis of the mantle's composition. The Earth has a magnetic field. The Earth's magnetic field is generated by currents inside that liquid outer core. And that magnetic field extends out into space, where it does a number of very nice things for us. So, as mentioned earlier, the sun is constantly spewing out particles called the solar wind. It would be bad if they slammed into us. But they get redirected by magnetic fields because they're charged particles. So charged particles are affected by magnetic fields, and the magnetic field of the Earth effectively acts like a trap. And these particles get trapped and bounce back and forth in bands of charged particles, forming what are called the Van Allen belts. So the magnetic field that extends out into space, and we can see the effects of the magnetic field sometimes when it's particularly charged, full of stuff, and that stuff hits the atmosphere, we get auroras. So if you've ever seen the Northern Lights, that's caused by the charged particles slamming into the atmosphere and causing it a series of things that cause it to glow. So this is the magnetosphere around the Earth. This is the region around the Earth where charged particles from the solar wind are trapped. The solar wind actually makes the magnetic field of the Earth not symmetrical. It sort of pulls it out behind it, blowing it out behind it. Earth's magnetic field is moderately sized. Jupiter's, on the other hand, is enormous. The tail of Jupiter's magnetic field actually extends all the way out to the orbit of Saturn. So we actually had a probe that was going to Saturn pass through the tail of Jupiter's magnetic field, and there was a sudden change in the instruments that they could detect because there was a sudden reduction in solar wind particles slamming into the probe. And these particles get trapped in areas that are called the Van Allen belts, where they spiral around the magnetic field lines. And this protects us on the surface from it. So if you don't have a magnetic field, you can add a lot of unfortunate things can happen from the solar wind. It can strip away portions of the atmosphere, things like that. And near the poles, the Van Allen belts can intersect with the atmosphere. The charged particles collide with atmospheric atoms, excite them, and you get a glowing light called an aurora. So these auroras are caused by oxygen and nitrogen in the atmosphere getting excited and emitting light. So we talked about excitation spectrums, those bright line spectrums, that's sort of what you're seeing here. So the Earth is a unique planet in a large number of ways. We can map the interior structure of the Earth using seismic waves. The Earth consists of a crust, a mantle, an outer core, and an inner core. And the liquid metal core generates the Earth's magnetic field. And similar things generate the magnetic fields of the other planets. So Jupiter's magnetic field is generated by the layer of liquid metallic hydrogen it has. And Mars doesn't really have a magnetic field because it's cooled down enough that it doesn't really have nice currents in its core. Things like that. So let's talk about Earth's surface and its atmosphere. So because Earth is in that range where it can have water and liquid water on its surface, that means our surface gets remodeled in a lot more ways than many other places. So there are three main types of rock that are observed on Earth's surface. There are igneous rock. Igneous means from fire. Igneous rock is volcanic rock. It formed from molten rock. So it either formed from lava cooling or from magma underground cooling. But you have liquid rock that cooled to form the rock. That's igneous rock. Sedimentary rock is rock that's formed of broken apart or deconstructed material from previously existing rocks. And this almost always involves water. Rock breaks into pieces, it's carried by water. These pieces are cemented back together by minerals dissolved in the water. That kind of thing. Or you have rock that's formed from just minerals dissolved in the water as the water evaporates away, things like that. The processes for sedimentation and sedimentary rock formation almost always involves water. So when we found certain types of sedimentary rock on Mars, that's part of how we knew there was water previously on Mars. Because they had to have formed under conditions with water. And then metamorphic rock is some previously existing rock that gets carried to somewhere with high pressure or temperature and changes. So you could have the sedimentary rock limestone. It's made of calcite. If that gets exposed to very high heat, it turns into marble. It recrystallizes to become marble. So that's some of the things that can happen. Earth also is somewhat unique in that it has plate tectonics. Its surface is constantly changing. The crust and the top layer of the mantle are floating on a more fluid layer of the mantle immediately beneath. And the Earth's surface is made up of about 20 or so plates that are moving around, running into each other. New material is being created, older material is being destroyed. So the plates move because of currents in the mantle. At the edges between plates, you get earthquakes, volcanoes, and mountains, but there are a few exceptions. The classic example is Hawaii. Hawaii here is in the middle of a plate. And you can actually trace the path. Hawaii is formed by, there's an upwelling of magma in the mantle that's just causing volcanoes over. And the Pacific plate has moved over that upwelling over time. And you can actually trace back the islands of Hawaii. So you have the current big island of Hawaii is the youngest, and they get older as you go along through the chain. And then there's actually a series of underwater old volcanoes that you can trace all the way back to Siberia, basically, where that hotspot used to be long, long ago. And there are other hotspots like Yellowstone National Park is sitting on a magma hotspot as well. And the person who first put together with good evidence this idea that the continents were moving around was Alfred Wegener. He noted the similarity of continent boundaries and the fact that there were similar fossils on widely separated continents in 1915. The actual explanation for what was going on and the acceptance of the idea of plate tectonics didn't happen until the 60s. But because the plates are moving around, so around 200 billion years ago, the continents were all combined into a single one called Pangaea. And this has happened multiple times in the history of the Earth. The continents are slowly spread apart and have formed their current structure. And the continents are still moving. The current boundaries are not permanent. They will continue to move. Some tears will occur in Africa, for example. India is still moving up into Asia. The Atlantic Ocean is steadily getting larger, things like that. Now, as the plates move around, where plates are separating, we get rift zones. So that's the middle of the Atlantic, has the mid-Atlantic ridge. That's forming new oceanic crust. The East African Rift Valley is a place where Africa is, the eastern part of Africa is slowly separating from the rest of Africa. Subduction zones where one ocean plate gets pushed under a continental plate. The western coast of South America, where the Andes are, is this So the Pacific plate is going under the South American plate. And it's melting. The melted rock rises up through the crust, makes volcanoes. That's what formed the Andes. Where plates move side to side at fault zones, you get earthquakes. That's the San Andreas Fault in California. Mountain building zones where continental plates are colliding and pushing up mountains. That the youngest one of those will be the Himalayas, which are still going up because India is still, the Indian subcontinent is still going into Asia. And then you get volcanoes. You can have volcanoes at hotspots under a plate, like Hawaii, or at a plate boundary, like Washington, Oregon, or Japan. That's where one plate is sinking under another and melting, forming volcanoes. So that's happening in Washington and Oregon. There's a small plate that's being subducted under the North American plate there. And it's also happening in Japan, where the Pacific plate and the Eurasian plate are interacting. And it's forming a volcanic island chain. So that's where all those volcanic island chains around the rim of the Pacific are from. So the Earth's entire surface is covered with crustal plates, which can move independently. And at the plate boundaries, you get lots of earthquakes and volcanoes, as you can see here, with all these dots for earthquakes and volcanoes. When plates move away from each other, you get rifts. And the oceans form and get bigger, and when plates slam into each other, you get trenches. And if you follow the continents drift backwards, the continents merge into one called Pangea. And that wasn't even the first time that it happened. There have been several supercontinents that have formed and separated throughout Earth's history. Turns out there's a few ways we can track the movement of continents over time, because you can get some information like from how rocks got magnetized as they formed and things like that. Then there's Earth's atmosphere. Earth's atmosphere is unique because it's got oxygen in it, but it's got 4 layers described by how temperature varies with altitude. The layer that most weather happens in and we live in, and where most of the atmosphere is the troposphere. That's the bottom layer. As you go up, the temperature decreases with altitude. This is where airplanes, most clouds, etc. are. Above this is the stratosphere, where temperature increases with altitude because of the ozone layer. The ozone layer absorbs ultraviolet light from the sun, and that warms the stratosphere. Above that is the mesosphere, where temperature again decreases with altitude. This is where most meteors burn up. And above the mesosphere is the thermosphere, which is the topmost layer, where the temperature increases with altitude, but it's super thin. You thin out. This is where auroras are. This is actually where the International Space Station is. And sort of the thermosphere peters out into space. So dry air is about 78% nitrogen, 21% oxygen, about 1% argon, and traces of other elements. Now, the amount of water vapor in the air can vary dramatically. So that's not, notice how this was dry air. You can go up to a few percent water vapor. The original atmosphere was methane, ammonia, water vapor, and carbon dioxide. That's the kind of stuff that comes out of volcanoes. It's from volcanic eruptions and maybe cometary impacts. But that carbon dioxide got converted into oxygen by photosynthesis. Weather is short-term variations in atmospheric conditions. Weather is what happens day to day. Climate is longer-term patterns, officially measured over 30-year time spans to smooth out variations, but you don't need necessarily look. The goal is to see longer-term trends. It's still useful to look year to year, but you're interested in sort of 1 year could be an exception, but you're interested in the long-term patterns. That's climate. So your weather could be, we could get very warm or very cold. The climate is the long-term pattern. And sometimes we have evidence of dramatic changes in the climate, long-term changes in the climate, which occur periodically. There's been ice ages, periods of glaciation, where much of the Earth's surface is covered in glaciers. There's been warmer periods as well. And it's thought that the long-term changes depend on what's called the Milankovitch effect, which involves the changing elasticity of Earth's orbit, so the shape of Earth's orbit changes over time slightly, and the changing tilt of Earth's axis. Because it turns out you don't need a huge change so the whole system of Earth is a little unstable. So if you get a little bit colder, you'll get more ice, which reflects more light, so you'll get colder. And that whole cycle will make it steadily colder. And the opposite is also true. You get a little bit warmer, you'll get more melting, more release of greenhouse gases and stuff. And it can feed the other way as well. So that's part of why people are so worried about our current human-caused climate change, is because we're afraid we might hit a tipping point. But also just because it's bad. It's causing all kinds of problems. Like we've had much more severe weather. We've had much more issues with that. We've had all that flooding recently. That's probably caused by the fact that it's warmer, so you get more rain, because warmer air can hold more water. The atmosphere. So here, this blue curve shows how the temperature varies as you go up in the atmosphere. And the pressure and the density just goes down as you go up. It gets thinner and thinner and thinner. Because that's just gravity. The pressure you feel from the atmosphere is just the weight of all the atmosphere above you. So you get less and less as you go up. And the troposphere is where it's thick enough for convection to take place, so it's responsible for weather. Pretty much all the weather happens down at the bottom. And convection, which drives weather on Earth, depends on warming of the ground by the sun. So the warm air rises, cool air will sink, and you'll get cycles. Those cycles are then, we have smaller scale local cycles, like a hot road warms up and cool air sinks on either side of it. We also have larger scale cycles, like the equator warms up more than the poles. So warm air rises around the equator and sinks at the poles. And then that gets affected by the rotation of the Earth to create cells. There's also the ionosphere, which is a layer ionized by solar radiation. It's a good conductor. You could bounce AM radio waves off of it, which is why AM radio can have go over surprisingly long distances, and how you can hear shortwave radio from like around the world, because it bounces off the ionosphere. But it's transparent to FM waves and TV. And then there's the ozone layer in the stratosphere, which absorbs ultraviolet radiation. Which is good because less ultraviolet radiation means less cancer for us. And one of the problems we had was that we were making chlorofluorocarbons, and releasing them into the atmosphere. They damage the ozone layer, resulting in a thinning of the ozone layer. It's referred to as the ozone hole, but it's really just a thin spot, which has been a negative. But actually, since chlorofluorocarbons were banned worldwide, the ozone layer has been recovering. Slowly but steadily. So it works. So worldwide, approaches to problems can work. And the surface of the Earth is not heated evenly. But sunlight that is not reflected by clouds or whatever is absorbed by the Earth's surface. It warms it, the surface then radiates that as infrared thermal radiation, and the atmosphere absorbs some of this infrared, causing further heating. And greenhouse gases, what we're worried about with climate change, are gases that are good at absorbing that infrared light emitted by the Earth. So these are things like carbon dioxide, water vapor, methane, stuff like that. They're good at absorbing infrared light. So they trap the heat on Earth. Now, having some greenhouse gases is good, because it keeps Earth from being freezing cold. But having too much, well, too much greenhouse gases leads to Venus, and a surface hot enough to melt lead. So nobody wants that. Now, it's not going to happen on Earth, but we don't want too much because it'll cause problems for us, because we're comfortable in a very thin range. So this is known as the greenhouse effect. Some of the sunlight gets reflected off, some reaches the surface and is reflected and then gets absorbed by carbon dioxide, water, other gases. Water is actually quite good at absorbing infrared radiation. And some will escape. And there's extremely strong evidence that the Earth is getting warmer. And the cause is fairly universally considered to be the burning of fossil fuels and the releasing of greenhouse gases by everyone who is actually a scientist, or is actually sensible about this. And so it's related, it's tied to the corresponding increase in carbon dioxide in the atmosphere caused by human industrial processes. The people who oppose this are in it for the money. So the Earth's surface is in a constant state of change. The moving plates cause volcanoes, earthquakes, rift valleys, etc. The atmosphere of the Earth has changed from its original composition. And the climate of the Earth changes over long periods of time due to astronomical effects. And another thing that has affected the Earth over time, let's see, has been large impacts. Maybe I'll go over a few of these things. So, are there craters on the Earth? Yes, there are 190 confirmed craters that are bigger than 100 meters across on Earth. The main problem with craters on Earth is they don't last that long compared to on other places. So craters on Earth get destroyed because Earth has very active erosional and geological processes that can wipe out craters. Also, sometimes it's hard to tell whether a crater was caused by an impact or a volcano. So, which leads to some funny things. There's a few craters that are named after, that have like volcanic implying names that are actually caused by impacts and vice versa. So there are erosional processes and geological processes that get rid of them. Smaller objects never make it through the atmosphere. Also, having a thick atmosphere protects you from smaller objects. And lastly, most of the surface of the Earth is water. When something hits the water, it splashes. It doesn't make a significant crater. But there are craters like this meteor crater in Arizona, which is one of the best preserved craters, impact craters on the planet. It's about 50,000 years old. Similar craters on the moon are literally billions of years old. So this is an impact crater. It's in Arizona. It's a Barringer meteor crater in Arizona. But large impacts have had major effects on Earth. So impacts happen. Small meteors burn up in the atmosphere every day. Eventually, some meteorites will strike the Earth's surface and do damage. Some of them will have massive airbursts, like Tunguska, but that happens every few hundred years. Over tens of thousands of years, a major impact can cause localized devastation. And over hundreds of millions of years, you get extinction level events, like the impact that killed off the dinosaurs. And not only are we certain that was caused by, that was at least associated with a meteor impact, because there's a layer of iridium, there's like a literal layer in the dirt of iridium from the impact. It's called like the KT boundary. You can actually in certain places see it as a literal line. Because there's a whole lot more of iridium in the ground that came from that meteorite. Because the heavier stuff would have sunk on Earth. And we found the crater. So it impacted off the coast of the Yucatan Peninsula in Mexico, in Ch7+Ch8+9. I can never remember how to pronounce the name of the place properly. But it's off the Yucatan Peninsula. There's a massive impact crater. There's evidence of the massive impact crater there that caused that impact. And I think that's it for today. We'll go back over impacts next time after the test, so that'll be next week. Remember, we have the test on Thursday. You need to be here in person to do the test. You get one sheet of notes. You can use both sides. And you need a pencil. I will have some pencils that I can loan out, but it'd be better to bring your own. So let me just pull back up those things. It's going to be 60 questions, multiple choice, using a Scantron sheet. So you need a pencil. You get one sheet of notes to use on the test, and you need to be in class to take the test. Do you have a question?
Would the worksheets and the homework be due like in the morning or like by the end of the day?
I think they're set to be due at midnight. And yeah, end of day.
So like Thursday night?
Yeah. So the worksheets need to be turned in by Thursday night. The homework, you can either turn it in class on paper or submit to the assignment. I accept late work. If you're a little bit late, like if you got it in late, technically early Friday morning, but it was late Thursday night, I'm not going to give you any penalty. I'm not super picky on that. But you know, if you're turning it in a couple days late, yeah, you're gonna get penalized. But I will always accept late work. So if you haven't finished it, do finish it and turn it in late, because some credit is better than no credit. And the penalty is usually 10%. So any other questions? Yeah, make sure you're here to take the test. Sorry about that issue with accidentally muting. I do not know what I did. But
Is the test tomorrow, like for the question, is it for like the whole textbook or like the session?
we should read the textbook. They're all questions from the text. But I mean, all the material is in the slides. Yeah.